It's just after 1:20 AM on the 26th of April 1986. You're a mechanic working in a nuclear power plant, and nearby some of your colleagues are running tests on another reactor. You notice they're having a bit of a problem earlier with it running slow, but whatever the trouble was, they seem to have fixed it, and now the reactor is working and the test is going ahead. Then, at 40 seconds past 1:23 AM, almost without warning, you notice they've hit the emergency scram button to shut the reactor down completely. A few seconds later, an explosion rocks the entire building, followed moments later by an even bigger explosion that rips the 1,000-ton cap off the top of the reactor and sends a jet of steam 3 kilometers into the atmosphere. The worst nuclear disaster in history has just occurred, and the name Chernobyl will go down in infamy. Whenever nuclear power is discussed, the Chernobyl incident almost invariably sits at the back of many people's minds. But what went wrong? Well, until recently, even I didn't know the answer to this question. So today, we're going to look at the science behind the disaster. And to do so, we first need to learn a bit about how nuclear reactors work. So, this is how you build a nuclear power plant. The first and arguably most important component of a nuclear reactor is the nuclear fuel. For most reactors, this is uranium, or less commonly plutonium, and it comes in the form of rods or pellets. However, you don't just want to leave these sitting around to undergo radioactive decay over time. Instead, we want a very specific nuclear reaction where a neutron collides with the nucleus of a uranium or plutonium atom. When this happens, the incoming neutron causes the atom to split apart into multiple smaller components. And this is where I'll introduce the most important concept in nuclear reactors: balance. This reaction creates 2 or 3 more neutrons, so if it goes on unchecked, a single neutron can create more and more reactions, and soon things get out of control. So the rest of a nuclear power plant is built to balance this out. You need to stop excess neutrons, but you also don't want to stop too many so that the reaction stops altogether. Normally, when we talk about whether a neutron will go on to create another reaction, we do so in terms of probability. When you average this across the entire power plant, or at least a single core, then we can deal with reaction rates. If the reaction rate is above 1, then the process speeds up. If the reaction rate drops below 1, then the reactor will slow down over time. The best way of stopping neutrons to go on to create more and more reactions is to simply absorb them before they reach the nuclei of another uranium atom. The most common method for doing this is using a control rod, which are made of materials such as cadmium that are excellent at absorbing neutrons. By inserting control rods further and further between fuel rods, they absorb more and more neutrons. By choosing where they sit, you can carefully raise or lower the reaction rates as desired. Maybe not so intuitive is the fact that the speed of a neutron plays a part into how likely it is to cause another nuclear decay. In fact, if a neutron is moving too quickly, then it's less likely to interact with another atom and perpetuate a reaction. So, a moderator is needed. All this is a material that slows neutrons down inside a reactor. They do this by simply bouncing the neutrons between atoms like a ball in a pinball machine. One common example of a moderator is known as heavy water. This is like regular H2O, except the hydrogens have 1 extra neutron. The reason you'd use this is that regular hydrogen containing 1 proton and 1 electron is great at absorbing neutrons, which is not the goal of a moderator, and you don't want water to do this inside a reactor. So instead, you use deuterated materials where the hydrogen now has 1 proton, 1 electron, and 1 neutron. The extra weight from these 2 neutrons gives the water its name, heavy water or D2O. The last important component is the coolant. This one's fairly self-explanatory. Nuclear reactions generate heat, and the coolant helps to draw that heat away to stop the core overheating. If heavy water is used as a moderator, it also often doubles as the coolant as well. Even if a reactor is shut down, it still requires a coolant, as uranium and plutonium will undergo natural decay anyway, which adds heat to the system. Incidentally, this is also why the Earth's core is still so hot. Natural uranium decay keeps it warm. If we put all these components together, we now have a working reactor. The fuel, control, and moderator are assembled together in the core. The fuel rods are suspended in the moderator, and the control rods are inserted in between these rods of nuclear material. The control rods are often attached to mechanical arms that allows them to be raised and lowered as required. In fact, if you've ever seen a nuclear reactor in a movie, generally it's the fuel or control rods that you see being manipulated. And nuclear reactors glow blue, not green, because the energy released matches that of blue light. Coolant is then pumped through this core, and the heat extracted can be used to drive a steam turbine. And in fact, this is how most power plants will generate electricity. And if heavy water is used as a moderator, then it often passes through a condenser where regular water is used to extract any excess energy before the D2O passes through the core again. Now that we've had a look at what a reactor generally looks like, let's have a glance at the Chernobyl reactors. The Chernobyl design is known as and I apologize for my butchering of the Russian, a reactor Bolshoi Moshchnosty Kanalny, or RBMK design, also known as a high power channel reactor. The RBMK design has one crucial difference that is key to understanding the Chernobyl disaster. Rather than using a moderator and coolant of heavy water, they use regular water and replace the moderator with graphite as shown here. This is primarily a cost-saving method, as heavy water is incredibly expensive to produce. So, what does this mean for the reactor? Well, remember earlier when I said that regular hydrogen is fairly good at capturing neutrons? Well, now we have a lot of it in the form of regular H2O flowing through the core of our reactor. So the water partially acts as a control rod. However, as the reactor gets hotter, or heats up as the reaction speed increases, then the water will also naturally get warmer. This means you can get bubbles or voids forming. If there's less water, then you reduce the chance of a neutron being captured before it finds another uranium atom. More voids is like partially removing a control rod. This effect is known as the positive void coefficient. What that means is as the reaction rate gets faster, this helps to further increase the reaction rate. Normally, however, this would be balanced by other things to stop the reactor getting out of control. Things like the coolant pumps running that helps push colder water in and voids out. The last thing I want to look at before we get to the disaster itself is xenon-135. That is xenon with an atomic mass of 135, and it's known as a neutron poison. What that means is that xenon-135 is great at absorbing neutrons, and in a nuclear reactor it can slow the reaction down. However, xenon-135 is not the direct byproduct of a nuclear reaction. Instead, it mostly comes from the decay of iodine-135, which has a half-life of 6.6 hours. What that means is that the xenon buildup inside a reactor mimics the reactor power from about 6.5 hours ago and not its current operating level. The xenon will naturally decay into cesium-135 over time or can be burnt off with neutrons, so it's normally relatively easy to manage inside a reactor. Now that we have all that out of the way, let's look at the disaster itself. The engineers at Chernobyl wanted to perform a safety test, which would show the plant would be fine in the event of a power failure. The test involved simulating a power failure by significantly reducing the output of one of the reactor cores. In this case, it was core number 4. What this would do would stop the heat reaching the steam turbines, which in turn would temporarily shut down the pumps running coolant through the cores before backup diesel generators kicked in. What the engineers hoped to show was that there'd be enough kinetic energy in the turbines that they would keep the pumps running until the generators had a chance to power up. This test had been conducted before, however it had not been successful. Also, they were going to go ahead and do this without consulting the personnel in charge of the plant's safety and after turning off the plant's emergency core coolant system. Going back to the 25th of April 1986, the engineers are about to shut down reactor core number 4 for routine maintenance, and so decide to take advantage of this to run their test. During the day, however, demand for electricity had been abnormally high and the plant had been operating above normal power for many hours. What this meant was that hours later, there was a build-up of our neutron poison xenon-135. Also, because of this extra demand for electricity, the shutdown of the reactor was delayed, and so was the test. After midnight, a new shift of engineers had started, unaware of the power requirements during the day. Because of the day's extra electricity demands, the test and the shutdown of the core were delayed. After midnight, a new shift of engineers took over, probably unaware of the day's energy demands. At 11 PM, the grid controller agreed for power to be reduced far enough for the test to be conducted. So the engineers began inserting control rods into the core to slow the reactor down. A power level of about 700 to 1000 megawatts of thermal energy was required for the test. However, because of the xenon buildup, the power suddenly dropped to only 30 megawatts of thermal energy. In an attempt to get the reactor working again, almost all the control rods were pulled completely out of the core, far more than would normally be allowed under safety regulations. The removal of so many control rods meant that by 1 AM, the power had increased back up to 200 megawatts. And this was decided to be close enough to the 700 megawatts that the test would be run anyway. So the engineers began shutting off valves to slow the turbines down. What they didn't realise was the engineers had just removed the delicate balance that all nuclear reactors need to have. Pulling all the control rods out meant that there was so much water in the reactor core that the positive void coefficient was now the dominant effect dictating the reaction rate. To put on top of that, the pumps that were now meant to keep the water circulating were also slowing down. So, as the xenon began to be burnt off, the water began to heat up. As the water heated up, voids began to form. This in turn made the reaction rate even faster, and that heated the water further, creating more and more voids. The vicious cycle of the positive void coefficient began to take over. Exactly what happened is not fully understood. What most likely happened is the following. At 1:23 AM, the test was started. The turbine stop valves were shut, and then the reaction rate began to skyrocket. 40 seconds later, the decision was taken to hit the emergency scram button. This initiated a full shutdown procedure where all of the control rods were going to be completely dropped into the reactor. However, another peculiarity of the RBMK design was that all of the control rods had small portions of graphite moderator at the bottom of them that sat inside the reactor like this. What it also meant was that there was a small amount of water below each of these graphite sections. This resulted in a fatal moment where for a few brief seconds the water, the neutron-absorbing water at the bottom of the reactor core, was replaced with graphite moderator. At 43 seconds past 1:23 AM, 3 seconds after the scram procedure had been initiated, the power exceeded what the reactor could sustain. Fuel elements began to rupture, and the steam pressure alone blew the 1,000-ton support cap off the top of the reactor in the first of 2 massive explosions. The steam then reacted with zirconium in the core to produce hydrogen gas, When this combusted, that gave rise to the second of the two massive explosions. It has often been said that the graphite moderator caught fire, however, this is not likely the case. Though, there have been papers out there that have argued what instead occurred was that the reactor went supercritical. This is the same mechanism as a nuclear bomb. Essentially, the plant blew up because of a small nuclear explosion. Without touching on the cleanup or the politics behind the Chernobyl disaster, it almost certainly shouldn't have occurred. So, does this serve as a lesson against nuclear power in general? No, almost certainly not. Most modern reactors are designed so that an accident like this cannot occur again, such as liquid salt reactors that are just meant to shut down if anything goes wrong. Although there still are RBMK reactors in operation today, though they themselves have undergone serious safety overhauls since the Chernobyl disaster. Though, if you want as a bit of extra information, the other 3 cores at Chernobyl stayed in operation for quite a number of years after the disaster, with core number 3 not being shut down until the year 2000. That being said, we can still learn a serious lesson from Chernobyl. Humans have long been good at making dangerous activities, such as flying or driving, relatively safe. And nuclear power is no exception. A better understanding of the world around us and a greater appreciation for the consequences of our actions are never a bad thing. Remember, I'm almost a doctor, and until next time, be like a proton. Stay positive.